Welcome. This is the video for Chapter 4 on utility. This chapter echoes quite a bit from the previous chapter, but introduces a little bit of the math. Okay. First thing I'd like to talk to you about is what is utility? We tend to talk about utility as if it was the same as happiness. And it's kind of the same thing and kind of not, but it's easy to slip into that language, and it's okay to talk about it that way. But you need to keep in the back of your mind that utility and happiness actually are not the same things. Utility, something has more utility than something else. Item A has more utility than item B. If, when presented with A and B, you choose A when you could have had B. That's all it means. Now, generally, we pick the things that will make us happier, but not always. There are times when we choose things deliberately, even though they're not going to make us happier. You're watching this video right now, and wonderful as entertaining as it is, you probably would be happier talking to your friends right now, or watching some other TV show. So utility is similar to happiness, but technically it's simply what we call the things that we choose over other things. Okay, reminder, preferences. We say that X is preferred to Y. Let's see if I can get this straight. There we go. Strictly preferred to Y with this symbol. The sort of curly greater than. This means that when presented with a choice of X or Y, the person whose preferences are represented by this will always choose X. This means that the person is indifferent between the two. They may randomly choose one or the other, but they don't care one way or the other. And this, we say that X is weakly preferred to Y. In the first one, we say it's strictly preferred. X and the symbol that looks like greater than or equal means that either X is preferred to Y or the person is indifferent between them. Now, a preference relation. That is the set of choices a person with this preference relation would make between different items. We'll choose A over B, indifferent between C and D, etc. Preference relations can be represented as a utility function if the preferences are complete, reflexive, transitive, and continuous. So here, we say that X1 being weakly preferred, actually, let's work from the bottom up. This person is indifferent between X prime and X double prime. If and only if, which is what that symbol means, the utility this person gets from x prime is equal to the utility they get from x double prime. Here we say that, let's call it x1 and 2. X1 is preferred, strictly preferred to x2, if and only if the utility derived from x1 is greater than the utility derived from x2. And x1 is weakly preferred to x2 if and only if the utility derived from x1 is greater than or equal to the utility derived from x2. Now, utility is an ordinal concept. A little bit of history. Early on, economists, when they were developing this concept of utility, tried to represent it as a cardinal number. That means that the difference between the two, the magnitude of the difference between two utilities, had some meaning. You could take the average of two. You could do various bits of math on it. So that if we said that you get 5 units, if your utility from this is 5, and your utility from that is 7, you could subtract and say, well, the difference, the amount by which you prefer the second over the first is 2. That doesn't work, frankly. So all modern economists, for several generations, many generations now, have, with very few exceptions, have viewed utility as a purely ordinal concept. To use the example before, you have two things. Thing A, you get 5 units of utility. The utility of thing A is 5. The utility of thing B is 7. From that, all we can tell is that if presented with these two things, the person will choose the second one. The person prefers the second one to the first. But how much more do they like the second than the first? Utility says nothing about that. This only is a concept of you prefer this over that, not by how much. Sometimes students have a little difficulty with this idea. Imagine you have a big balance scale like the one I'm showing you here. Now you want to know how much people weigh, or weigh people. Why not? So, and this is a big scale. You can have somebody sit on the right side and somebody sit on the left side, and depending on which way it goes, you can determine who weighs more or less than whom. But you don't have any standardized weights. You don't have any, oh goodness, whatever, any objects like this that you know weigh exactly 1 pound. If you had a bunch of them, then you could weigh a person in pounds. You know, put them on the one side and see how many of these you have to put on the other. 152 of them, then you know the person weighs 152 pounds. But you don't have any of those. So all you can do is put people on and see who weighs more or less than whom. Now let's say you wanted to create a measuring scale, not scale like the physical one, I mean scale of units. You could go out and find a whole bunch of rocks and put the rocks, one on each side on the scale, and doing that way, you could find a whole bunch of rocks that all weigh the same amount. You don't know how much each one weighs, but you know they're all the same. So you have this big pile of rocks that all have the same weight. Well, now you could have somebody climb into one bucket and you could put rocks from your pile in the other bucket, and you could say, this person weighs 141 rocks. And then you could weigh somebody else. Say, this person weighs 146 rocks. Okay. But there's nothing special about the unit of a rock. If you took the day off, went somewhere else, took all your rocks with you, because why not? Somebody else could come in and do exactly the same thing. They would get the same results of who weighs more than who, and if they went out and got some rocks, they could do the same thing you did. But their rocks would not weigh the same as your rocks. So the person you weighed with your rocks and said, this person weighs 142 of Bob's rocks. But the person who's doing this the next day might say, this same person weighs 370 of Susie's rocks, if Susie was a person doing it. So the numbers would be completely different. But they would still tell you the same way who weighs more than whom. If you measure a person in 1 unit, pounds, or kilograms, it doesn't change the information, but it does change the numbers. So we construct utility functions with numbers, just like the numbers of rocks. But the only thing these functions describe are which bundle of goods provides more utility than the other, not by how much. All right. Consider these 3 bundles. And suppose, let's call them bundle 1, 2, and 3. Now suppose a person prefers, that'd be bundle 2, to bundle 1, strictly prefers. And they're indifferent between bundle 1 and bundle 3. Well, you can assign any numbers to the amount of utility derived from each of these, and it will describe the exact same choices and the exact same preferences as long as the order is preserved. For example, you could say that the utility provided by bundle number 2 is 6. And the utility provided by bundle number 1 is the same as the utility provided by bundle number 3. They're both 4. Okay. This bundle, because it has, in our numbering system, 6 utility units, means you get more happiness, more utility, loosely speaking, out of that bundle than either of the other 2, because that number is 4. But you could put different numbers here. Instead of 6, 4, and 4, it could be 10, 3, and 3. It could be a trillion, 1 and 1. They all represent the same preferences. Okay. An indifference curve is the set of all consumption bundles that you are indifferent between. Well, if you're indifferent between them, that implies they have the same utility level. So all bundles on a given indifference curve have the same utility. Now, the next few slides here represent a little formal, more formal, and certainly better drawn version of what I tried to talk to you about in the last lecture, about how indifference curves are a simplified way of representing a multidimensional function. So, here, x1 is some commodity, apples, whatever. x2, another one, oranges. Therefore, all of these points in this plane represent a particular consumption bundle. For example, this red one represents 4 apples and 1 orange. And we can say, now going to the third dimension, that bundle gives 4 units of utility. Utility level 4. Well, 2 apples and 2 oranges also provide 4 utility units. Utility level 4. Therefore, we know that a person, if given a choice between these 2 consumption bundles, would go, don't care. They're the same to me. But this one, with 2 apples and 3 oranges, utility level 6, they would strictly prefer that over either of the other 2. If you connect together all the points in 3D space that represent the same level of utility that a consumer is indifferent between, you get indifference curves. The higher the curve, the more utility it'll be preferred. Now, this slide and the 8 that follow sort of show this 2-dimensional to 3-dimensional relationship. So I'm going to go through this twice. This is the traditional 2D presentation of indifference curves. Now I'm going to start rotating it. Let me do that again, but a little bit faster. See, it's this 3-dimensional function is just indifference curves when you're not looking straight down on them. Okay. The collection of all indifference curves for a given preference relation constitutes an indifference map. An indifference map is equivalent to utility function. Now, because utility is ordinal, you can transform a utility function in any way you want. And it will describe the exact same set of preferences, so long as your transformation preserves the ordering. Here's an example. Let's say that you have 2 commodities, x1 and x2. And let's say the utility function describing your preferences is this: x1 times x2. The number of x1 you have times the number of x2 you have yields a number, and that will represent your utility of that particular bundle. Okay, for this particular bundle, 2, 3, 2 units of the first, 3 units of the second. Well, 2 times 3 is 6. The utility of this consumption bundle, 4 units of the first thing and 1 of the second, well, that's 4 times 1, that would be 4. And if you have 2 and 2, it also gives 4. Now, since the utility you get from this bundle, 6, is greater than the utility you get from either of those, it means that you strictly prefer, the first bundle over either of the second 2. And you're indifferent between the second 2 because they both, from this utility function, have a utility of 4. However, that is not the only utility function that can describe exactly the same preferences. This utility function here, x1 times x2, does describe the choice structure, the preferences of a person who prefers 2 and 3 over the other 2 bundles and is indifferent between the second 2. Let's create a different utility function. We'll call this one, instead of u, we'll call it v. Utility function v is going to be the square of utility function u. Therefore, utility function v is the square of the number of x1s you have times the square of the number of x2s you have. So, the utility in this utility function of 2 of the first thing and 3 of the second would equal 36. And the utility of these 2 would each be 16. Well, again, it orders them the same way. The transformation of squaring the first utility function preserves the order. Assuming that utility in the first case is all positive, and we define it as positive here. So squaring it is a monotonic transformation. It preserves the order, and therefore, whether you want to describe this person's preferences as the utility they get from their choices as x1 times x2 or x1 squared times x2, it describes exactly the same preferences. The numbers change, but the preferences described do not change. Just like if you were weighing people and you use different size rocks, the number of rocks that a person weighs will change, but how much they actually weigh and who weighs more than who does not change. Okay, here is another monotone transformation. This utility, whoops. There we go. This utility function does describe still this preference relation. Now let's take that utility function and make a different monotonic transformation. It'll be 2, this new utility function w will be 2 times that function plus 10. Well, if you just plug in the numbers, again, you get different utility numbers for each of the bundles, but still, the preference ordering does not change. This, again, shows that any function that describes the choice architecture, the preference relations of a set of choices, can be transformed in an infinite number of ways. and represent exactly the same choices, exactly the same preferences, so long as your transformation doesn't change the ordering. Monotonic transformation. Now, I think I mentioned this briefly in the prior lecture. We talk about goods in econ, and most things are goods that we deal with commonly. But a good, by definition, is something that getting more of it gives you more utility. Not all things do. I think the example I used last time was garbage. Well, garbage is a bad. A larger quantity of it gives you less utility. And a neutral is something that does not change utility with additional consumption. And some things change. Actually, most things change from goods to bads, depending on the quantity. Water. Little bit of water, and you get a little more water, you're happier. More water, you're happier. Ooh, I've got even more water. Yay, I'm thirsty. But there is a point at which an additional quantity of water will actually make your utility go down. You might call that drowning. So, things are neither goods, bads, or neutrals all the time. It can depend on circumstances. It can depend on quantities. Okay, some common utility functions. This is the one we were looking at before. Now let's look at this one, where utility is simply the number of x1s you have plus the number of x2s. This is a very simple example of a utility function that are perfect substitutes. You can have A or you can have B, and you don't really care which, you only care about the total of them. This is what indifference curves for perfect substitutes look like. Now, remember, I mentioned this last time. The defining characteristic of perfect substitutes is that the indifference curves are linear. They are lines. They don't curve. Not that they have a 45-degree angle. For example, here, you could have that utility function, where your utility is how many of x1 you have, whoops, I'm in your way, how many x1 you have, plus 3 times how many x2 you have. This shows perfect substitutes, but at a 3-to-1 ratio. The book, I think, in all cases, gives examples of things that are perfect substitutes at a 1-to-1 ratio, but that's only one case. All right, perfect complements. These are things that you want to consume together. The most basic example in every textbook in the world is right shoes and left shoes. Not perfect, but complements peanut butter and jelly. Okay, I want to mention about this mathematical notation, min curly brace x1, x2. That means that that number is whichever of the things in the braces, x1, x2, is smaller. If x1 equaled 5 and x2 equaled 3, then this entire term evaluates to 3. So, what do the indifference curves of perfect complements look like? If they're perfect complements, they will always be a right angle. Again, the example of shoes, if you have 3 right shoes and 3 left shoes, well, giving me 2 more left shoes, so you'd be at 5, 3, it doesn't get you any more utility. Okay, quasi-linear utility functions. A quasi-linear utility function, all it means is that utility is linear in one of the terms. For example, utility of our old friend commodities x1, x2 is some function of x1 plus x2. It's linear in x2. Here's an example of that. Now, for x2 here, this can also be, for example, that does not change that this utility function is linear in x2. Give me 1 more x2, and I will get 9 more utility units. But that's still linear. For the first unit, for the second, for the millionth unit of x2, each one will increase my utility by 9. Again, leaving the coefficient as 1, as we see here, it just makes the analysis a bit simpler. And this is what they look like. Now, these indifference curves, notice that how much extra utility you get as x1 increases, well, that's a curve. But every time you get an extra unit of x2, your utility goes up by the same amount. It's just the same curve, just displaced, translated vertically. Okay, Cobb-Douglas utility. This is probably the most important utility function. It takes this generic form. It is the number of units of the first thing raised to some power times the number of units of the second thing raised to some power, with both of those being strictly positive. Here are some examples of it. If the exponents, which we call a and b, are both 1/2, then you'd have x1 to the 1/2, x2 to the 1/2. A could be 1, B could be 3, and you would get that. The reason why Cobb-Douglas utility functions are used so much in econ is because they describe well-behaved preferences. The indifference curves you see in Cobb-Douglas utility functions are convex, monotonic, transitive. Actually, let me back up. Because any monotonic transformation of a utility function represents exactly the same preferences, just essentially in different units, loosely speaking. Cobb-Douglas utility functions are frequently written in this form. so that the exponents add to 1. Any Cobb-Douglas utility function can be rewritten in this form representing the same preference architecture. Now, marginal. You should remember what marginal means. It means incremental. The change caused by one tiny bit of more or less of something. Marginal utility is how much additional utility you get from one small change in the quantity of a thing. The marginal utility of item I is the change in total utility for a change in quantity of X. It's a derivative. Now, you'll notice here that some of you have only taken single variable calculus. Some of you have taken multivariable calculus. For those of you who have only taken single variable calculus, do not panic. If the function is u, we would, in single variable calculus, write it this way, the derivative, du dx. But notice we're using a slightly different symbol. Sort of a, I'm not drawing it well, it's more like that. Sort of a curly D, the top comes over a bit. This represents the partial derivative of the function. This is the derivative of u with respect to x. This is the partial derivative of the function u with respect to x. Partial derivatives are really simple. If you know how to take a simple derivative, you know how to take a partial derivative. It's just one tiny little difference. But for those of you who are not familiar with it, on Moodle, near the top of our Moodle page, I've posted links to 2 brief explanations of what a partial derivative is. One's a video, 10 minutes. The other is just one web page, easily in a half hour. You can master this. It just means that this is the change in utility caused by an incremental change in commodity Xi if there are multiple commodities. Let's see if I can give you a more concrete example. Okay. Unfortunately, these PowerPoints were given to me by the publisher, and then I doctor them up. This one, the typesetting of math is rather poor. Remember from single variable calculus that the derivative, one interpretation, is just the slope. Well, in a multivariable function, the derivative is still just the slope. But if you're dealing, remember, with two commodities, this is a 3-dimensional function. So you don't just have y equals x. You have, very loosely, y equals some function of, actually I should keep that consistent. Z, the vertical component, of our drawing, equals some function of x and y. So the inputs are x and y, and the output of this function is z. Now, if you have a three-dimensional surface, picture that, the utility mountain, and I ask you, what's the slope right here? Well, because it's in multiple dimensions, you have to ask, well, the slope in which direction? Imagine you're standing on the side of a mountain. If you walk straight up towards the peak, maybe it's very steep. Let's assume the mountain is nice and symmetrical. But if you, at the same point, walk parallel to the ground, just walk around the peak, maybe you're not going up at all. Maybe the slope in that direction is 0. So when you have a multivariable function, derivative is still slope, but you have to say in which direction, roughly. So here, if you want to know the marginal utility of commodity 1 in this function, that is, if you get one more of this thing, how much is your utility going to go up or down? Well, then you have to take the partial derivative, the derivative just with respect to x, the derivative essentially in the x direction, the x1 direction. The way you take a partial derivative, and look at the little video I posted, it explains it very easily. If you take the partial derivative of a function with respect to a particular variable, in this case x1, you just pretend that all the other variables are constants. The derivative of a constant is 0. So let's see if I can replicate what they do here, but in a little more easy to see fashion. Okay. The marginal utility of item 1, I'm going to change it from x1 and x2 to x and y. Just makes it a little easier to see. So the derivative, the marginal utility you get from more of x is the partial derivative of the utility function with respect to x. Now, if this is your utility function, which I'll change to be x to the 1/2 y squared, just to make it a little visually more clear, to take the partial derivative of that function with respect to x, well, you pretend that any variable other than x is just some constant. You don't need to know what, just it's a constant. So here, x is the variable we're taking the derivative of. What is that? Y? It's some constant. Well, then we can take the derivative of that easily. I'm going to switch the order to make it a little more obvious. Y squared x to the 1/2. All right, what is the derivative of a constant times x to the 1/2? Well, if y squared was 3, then it would be 3 times the derivative of x to the 1/2. The constant just goes along for the ride in this case. So it'd be the same thing. The derivative would be, well, that constant times the derivative of x to the 1/2, which would be 1/2, you bring that down, times x, subtract off 1, negative 1/2, which is what they have there with, well, very bad typesetting, so it's hard to tell which is in an exponent. But 1/2, that's there, x, well, they call that x1, to the minus 1/2 power times x2 squared. All you do is pretend everything you're not differentiating with respect to is a constant. Now, if you wanted to take the partial derivative of x2, excuse me, the partial derivative of the utility function with respect to commodity x2, well, x1 to the 1/2 x2 squared. Now we're going to view, because we're taking the derivative with respect to x2, we wanted the slope in the x2 direction, we just view any variable. Is it an x2? No? Then it's a constant. So the derivative of a constant times x squared is just a constant times 2 times x, which is what they have there. Okay, so that's how you take the partial derivative to calculate the marginal utility of commodity 1 and the marginal utility of commodity 2. The general form for indifference curve is this, where k is a constant. Notice there are 3 little cross bits instead of 2. That means it's a definition. So any quantity of x1 and x2 that gives you exactly k utility has to be in the same indifference curve. Here, the partial derivative with respect to x1, so how much the function changes with a small change in x1 times how much you change x1 plus how much the function changes with respect to x2 times how much you change x2. So this is the total change in utility. Well, if you're on an indifference curve, that has to be 0. So they have the same utility, which is what we see there. Now, if you rearrange this, you get this, which I'll try to write a little larger, and du dx1 over du dx2. This is the marginal utility of x1 over the marginal utility of x2, which is the marginal rate of substitution. The top half, how much extra utility you get for a little change in x1. The bottom, the denominator, how much change in utility you get for a small change in x2. The marginal rate of substitution is the ratio at which you are willing to trade these things off. So, suppose this is your utility function. Then the partial derivative of this function with respect to x1 is, well, the derivative of x1 is 1. x2 is a constant, so it would be x2. And it works just the other way for the other one. So, the marginal utility of x1 is x2, and the marginal utility of x2 is x1. The marginal rate of substitution is the ratio of the marginal utilities, with a negative out front, because if you get more of one thing, you have to have less of the other. That is the marginal rate of substitution between x1 and x2. Now, as mentioned before, because utility is ordinal, any monotonic, that is, order-preserving transformation of a utility function describes exactly the same preferences. So if you perform a monotonic transformation on a utility function, what happens to the marginal rates of substitution? The short answer is nothing at all. Think of it without the math for the moment. The marginal rate of substitution, the rate at which you're willing to trade this, units of this for units of that. You can express that preference with any math you want. Multiply the utilities by 1 billion. Well, it still describes the same choices, the same preferences. Therefore, you're still willing to trade off units of this and that at the same ratio. The math doesn't change your preferences. So, for this utility function, the marginal rate of substitution is that. Create a new utility function describing the same choice behavior. A monotonic transformation, square it like we did before. Then the new utility function is that. What is the marginal rate of substitution for this new utility function? Well, I won't bore you with it. You do the math, it comes out exactly the same, except there's a 2 in the numerator and a 2 in the denominator, which cancel out, which leaves you with the same thing. Because a monotonic transformation describes the same preferences, the marginal rate of substitution has to be the same, because that's the ratio at which you're willing to trade off this for that. Oh, that also means you have a way of determining whether two utility functions describe the same choice behavior. Even though the numbers look very different, well, calculate the marginal rate of substitution of each of them. Take the partial derivative of commodity 1 and commodity 2, put them in a fraction. For the first function, do it for the second function. If you get the same answer, the two functions are describing exactly the same preferences. That's it for today. See you next time.